Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to the last lecture of Algebraic Topology. So in this lecture we will basically be reviewing what we have done in this course, and we will try to take an overall view that what we have achieved so far. So we will be doing a lecture by lecture review of the course, and then at the end we will discuss that what are our achievements in this course and what we can do further with this set of tools that we have learned in this lecture. So if you remember, then in lecture number 1 we went back in time and we discussed some basic concepts that helped us throughout the course. So starting from very basic idea of sets, and then we discussed group in a very detailed way, and if you remember that at each and every step we have been using the idea and the concept of groups. Okay, so for example in the last lecture where we discussed the relation between the covering spacings and the fundamental group, we used the idea of group actions. Okay, and then we used left cosets as well as other things. So till our last lecture we have been using the idea of groups, because when we are studying algebraic topology, then we are associating topological structures with some algebraic structures, and those algebraic structures are most of the time groups. Okay, so that's why we discussed groups in our lecture number 1 in a detailed way. And then in lecture number 1 we discussed what are vector spaces and linear transformations. Of course you know that where we used it, of course, when we were trying to define simplices, and which of course helped us to define simplicial homology. Okay, so that's why we needed these things. So in lecture number 2 we started with some technical language of this course called the category theory. Okay, so once again if you remember that we have been using the idea of categories and functor till our last lecture. Okay, so we have used for example the functor pi1. Okay, so the functor related to the fundamental group, and we have used some other categories, so categories of pointed topological spaces, categories of abelian groups, categories of groups, and categories of just topological spaces and other categories. Okay, and in this lecture we just define the basics of categories and what are functors, and this provided us with some technical language that we used throughout this course. Okay, so in lecture number 3 we started with the very basic definition of algebraic topology called the homotopy. Okay, so before this we defined some basics of topology, and of course we need some basics of topology in this course, because we want to discuss topological structures using some algebraic machinery. So the very first you can say non-trivial definition was homotopy. Okay, so we know what is a homotopy. If you have a function f and a function g, then they are homotopic if one of the function can be continuously. Okay, so we are emphasizing on the word continuously. Okay, so if one of the functions, for example f, can be deformed continuously into the other function g. Okay, so notice that I have fixed the endpoints, and later on we defined this thing to be relative homotopy, but in this lecture we didn't impose any condition like this. So in this lecture we just defined that okay, this is one function f, and this is second function g, and if we can deform this function g into the function f or f into g continuously, then they are homotopic. Okay, so this idea of homotopy helped us once again throughout this course. Of course, if you remember, then till our last lecture we have been using the idea of homotopy. Okay, so when we try to discover the relation between the covering spaces and the fundamental group, we used this homotopy, and we discovered some facts, okay, about the fundamental group of a base space and its relation with the fundamental group of the covering space. Okay, so in lecture number 4 we continued with our discussion of homotopy. Okay, and then we defined what is a homotopy category. Okay, so this is a quotient category of the category of topological spaces. Okay, and so using this category, most of the ideas were simplified. Okay, and then we went on to define what is quotient topology. It's a very simple idea. So in quotient topology we define an equivalence relation, and that equivalence relation gives us a quotient topology. So the idea is very simple. Okay, so for example, if I have a square, then I can define an equivalence relation which will identify the opposite points of these sides and the opposite points of these sides. Okay, so this whole side is identified with this side, and this whole side is identified with this side. Okay, if we can do that, then basically we will get a torus. And similarly, we can obtain other structures using this idea of quotient topology. Okay, and once again, needless to say that we have been using this idea, this notion of quotient topology again and again throughout our lectures. In lecture number 5, we discussed what is path connectedness, and we discussed this functor. So notice that I have said earlier that in lecture number 2 we discussed what are categories and what are functors, and notice that we have been using these things again and again in our lecture notes. Okay, so what is path connectedness? So a space is path connected if you can find a path between any two points in the space. Okay, so for example, in this diagram you can see that it is path connected and it is not path connected. So why it is not path connected? Because I cannot find a path from this point, let's call it x, to the point y in this topological space. Okay, so it is not path connected, and this space is path connected. Okay, and if a space is not path connected, then there exist path connected components. Okay, so for example, there is 1, 2 and 3 path connected components. So in other words, you can say that the maximal path connected space, subspace of a space X is basically a component, a path connected component of that space. Okay, so the biggest set which is path connected is one path connected component of X. Okay, so in this case there are 3 path connected components. Now this functor pi naught helped us to find the number of path connected components of a topological space X. Okay, moving further on, we discussed what are simplexes. Okay, so before defining simplexes, we defined what are affine spaces, and then we defined what are simplexes. Okay, so the example of simplexes include, for example, starting from a point, and then we have for example 2 points, let's call it P0 and P1, then this form is simplex. And similarly I can construct other simplexes as well. Okay, so this shaded 2 triangle is another simplex. Okay, so let's call it P0, P1, P2. Okay, so of course now we know that why we defined simplexes. We are going to need it to define the simplicial homology. Okay, so what is simplicial homology? We shall see it in a moment, but the simplicial homology is one of the tool to discuss the topology of a topological space. Okay, so that's why we needed these simplices. So why we defined affine spaces? Because we are going to need this to define simplices, because simplices live inside affine spaces. Okay, so in a very simple way, when we say affine spaces, we can easily take it to be Rn. Okay, so if we are working on real numbers. Okay, moving further on, we define what is fundamental group of a topological space. Okay, so this is one of the very important ideas of algebraic topology. Okay, so this is the thing that connects topology with algebra. Okay, so give me a topological space, I'll give you some group associated to it. Okay, so that's why this is one of the very important concepts of algebraic topology. So in other words, this is our first bridge that connects algebra with topology. Okay, so one of the simple bridges connecting topology with algebra. And then we have the discussion of simply connected spaces. Of course, we know what is a simply connected space: a path connected space whose fundamental group is identity. Okay, at each and every point. So I shouldn't say at each and every point, because if it is path connected, then the fundamental group at each and every point is the same. Okay, so what is a fundamental group? Okay, and why we need this fundamental group? So remember, we want to discuss the topological properties of a topological space X. So for example, if I have a torus, then I want to differentiate this torus with this sphere. So how to differentiate a torus with a sphere? So the idea is to take care of the loops, okay, which are unique in some way. So unique in what way? So for example, if I take this loop on a torus, then just consider this loop is made of some sort of thread. Okay, and it is fixed at this point, at this node. And now if it is lying on this torus like this, then I can squeeze this thread and it will just become a point. Okay, so in other words, we can say that this loop which lies on the torus is homotopic. Okay, can be continuously deformed to this one point, or in other words, a constant function. Okay, so we can say that this loop is homotopic to a point. Okay, so or a constant function. So but if I consider another loop which goes like this along the torus, then once again consider this loop made of a thread, then if I squeeze this thread, okay, so now it's passing over this thing. Okay, so if I squeeze this thread, then it has to leave the torus, and since it's a thread, or it's a path inside a torus, it's a loop inside a torus, so I don't want this thread to leave this torus, because it will no more be a path inside the torus. So I cannot squeeze this thread so that it becomes just a point. Okay, so that's a unique thing about this loop, which is basically depicting some topology of this space, which is the torus. And similarly, of course, I can take other loop, so going like this, And this loop once again has the property that if I squeeze this loop, then it will not become a point. So, and we can also see that I cannot deform this loop. So let's call it gamma 1 and let's call it gamma 2. So gamma 1, I cannot deform gamma 1 into gamma 2. Okay, so there is no continuous way of deforming gamma 1 into gamma 2. Okay, so that's why this thing tells us that we are talking about torus. Okay, so we cannot observe this thing for example on a sphere. Okay, so take any loop on this sphere. Okay, so take any loop on the sphere, we can squeeze this loop to just one point. Okay, so take any other loop and it will just become a point. So in other words, the fundamental group is trivial in this case, and we can also see that this sphere is path connected, so we can say that it is simply connected space. So that's how we can differentiate a torus from a sphere by just looking at loops. Okay, so that's one of the important things. Now the point is there are some restrictions on this fundamental group. So for example, is it true that it can differentiate between two spaces of higher dimension? Okay, so remember we have been discussing these surfaces in for example in real R3. Okay, so we can differentiate between a torus and a sphere using the fundamental group. Is it true that the fundamental group can differentiate between two higher dimensional objects? So unfortunately the answer is no. Okay, so that's why we are going to need some further machinery in order to differentiate between two spaces of higher dimensions. Okay, so for example, if you remember that the fundamental group of sphere, okay, so all Sn when n is greater than or equal to 2 are simply connected. So in other words, the fundamental group is trivial. So there is no way that we can differentiate between Sn and Sm where m is not equal to n. So there is no way that pi 1, this fundamental group, can help us to differentiate between these two different topological spaces. So these are the restrictions on this idea of fundamental group. Okay, so let's go on and let's try to see that what we did in order to rectify this problem. Moving further on to lecture number 8, we defined what is the functor pi 1. Of course, this is the functor related to the fundamental group. And then we discussed some techniques for calculating the fundamental group. For example, we calculated the fundamental group of Sn where n is greater than or equal to 2. Okay, and basically we proved that it is identity. Okay, and then we also calculated, for example, the fundamental group of a torus using the product topology. Okay, and then we used this thing, for example, to show that R2 is not homeomorphic to Rn where n is not equal to 2. Okay, so that's how we use this algebraic structure, which is a group, to understand the topological structure of some topological spaces. Okay, and then in lecture number 5 we proved this non-trivial result that the fundamental group of a circle is basically Z. Okay, so it took most of the lecture 9 to prove this result. Okay, and then in the last portion of this lecture we defined what is a topological group. Okay, and remember that we used this result for example, when we were discussing the covering space of a circle. Okay, so in this diagram you can see that it's a circle and it is the covering space of a circle. Okay, and more or less the idea is the same when we were trying to calculate the winding number. Okay, so the winding number is how many times we are circling around the circle. Okay, and moving on, we in lecture number 10 we defined or we started our new topic, which is the simplicial homology. So we remember that simplicial homology is one of the simple kinds of homology that we can calculate, and the calculation of simplicial homology is very algorithmic. So in other words, if we want to calculate simplicial homology, then we can also use a computer. We can program and we can use computer to calculate the simplicial homology of different topological spaces. Of course, there are some restrictions on each and every technique, and in this technique, of course, the condition is can we have a simplicial complex, okay, so that can represent that topological space. Okay, so can we triangulate a topological space? So that's the question. Okay, and of course in this lecture we discussed this idea of triangulation as well. Okay, so in this lecture what we did mainly, after defining the simplices, we defined simplicial complexes. Okay, so what are simplicial complexes? It's a special union of different simplexes. Okay, so for example, this is a simplicial complex. Okay, so what is not a simplicial complex? So this is one vertex, second vertex, third vertex. Okay, so if we go like this, and this is not a vertex. Okay, so we can see that it is not highlighted, so this is not a vertex. So if the intersection of this simplex and this simplex is not, okay, so if their intersection is not a simplex, then it is not a simplicial complex. Okay, so it is not a simplicial complex and it is a simplicial complex. And then of course, as I said earlier, that we need this idea of triangulation, so that I can know that for which topological space I can calculate the simplicial homology, and for which topological space I cannot calculate the simplicial homology, or for which topological space it is extremely hard, it is difficult to calculate the simplicial homology. And as we move on, we will go to singular homology, and we will go to cellular homology. And of course we know that the cellular homology, in some cases, if we can understand the CW complexes and the cell structure of topological spaces, then cellular homology is relatively simple than simplicial homology. But once again, both of these techniques have their own advantages. So for example, simplicial homology can be calculated in an algorithmic way, so we can train a computer to calculate the simplicial homology for us. Okay, and of course in lecture number 11 we defined what is a simplicial homology using the simplicial chain complex. Okay, so we have a chain complex, and in this chain complex we have at the nodes we have free abelian groups, and then we have boundary maps, and we use this chain complex to define simplicial homology. Okay, and moving on to lecture number 12, we discussed some techniques of calculation of simplicial homology. And here we also discussed this quotation that homology, an idea whose time has come. Okay, so it is simple to apply. It will it can discuss the topology of a structure in a very easy way. Okay, so in this diagram you can see that there are different antennas, and for example we want to discuss the topology, we want to discuss the area which is covered by these antennas. So we want to discuss the topology of the area covered by these antennas. Of course the simplicial homology is the answer, because once again, due to its simplicity in the calculation. Moving on to lecture number 13, we discussed how to calculate simplicial homology. Okay, and we present different techniques for the calculation of simplicial homology. Moving on to lecture number 14. So as you remember that I used the word of chain complex when we said that how to define simplicial homology. So what is this chain complex? So this is coming from, so this is a terminology from homological algebra. So that's why we are going to need this homological algebra for the calculation of each kind of homology. Okay, so whether you are calculating simplicial homology or singular homology or cellular homology, we are going to need the idea of chain complexes, we are going to need the idea of modules, we are going to need the idea of fields and rings and other ideas from homological algebra. And that's why we had this review of homological algebra in our lecture number 14. In lecture number 15, we continued our discussion of homological algebra, and we discussed what are short exact sequences. Okay, and then we discussed what is a 5 lemma. Okay, we also did some proofs of some of the results. So what is a short exact sequence? We know that a short exact sequence is of the form A goes to B goes to C goes to 0. Okay, so over here we assume that the image of this map, let's call it F, is equal to the kernel of this map G. Okay, and if we assume that this holds, then it is a short exact sequence. So once again, if you remember, then we have been using this idea of short exact sequences again and again throughout our lecture notes. So moving on to lecture number 16. We discussed what are chain complexes. Okay, so once again, why we are going to discuss chain complexes, because whenever we define homology, we start from constructing a chain complex. Okay, so in simplicial homology we constructed a chain complex where the nodes are free abelian groups. Okay, and the maps are the boundary maps. Okay, so moving on to lecture number 17, we defined homology groups of simplicial pairs. Okay, so a simplicial pair is basically a simple idea where we have a subspace of a topological space, and these two spaces, okay, so with the relation that A is subset of X. So this helped us in calculations of some simplicial homologies for some topological spaces. Okay, so in other words, you can say that this is just another tool for calculations of simplicial homology. Okay, so moving on to lecture number 18, we defined calculation and definition of homology. Okay, so we also defined what is Euler characteristic, and we define what is homology of a torus. Okay, and then we give the axiomatic definition of homology. Okay, so I have been saying three different names again and again: simplicial homology, singular homology, and cellular homology. So what is the difference between them? Okay, so in this lecture we discuss that what is homology, in other words the axiomatic definition of homology. If some homological theory, okay, so for example singular homology or simplicial homology or cellular homology, if it satisfies these axioms, then we say that it is homology, otherwise it is not homology. Okay, and as a matter of fact, singular, simplicial and cellular homology satisfies these axioms, so that's why we can say that this is the homology. It's just the matter of calculating the homology, which differs in the techniques, but eventually we are calculating the homology. Okay, so it is the same thing. Okay, so this axiomatic definition emphasizes on the fact that we are calculating the same thing, which is homology, and it's just the matter of the method which we choose to calculate the homology. Okay, and as I said earlier that we calculated the homology of torus, and it was a little bit non-trivial to calculate the homology of torus using the simple shell homology. Okay, as we will move on, we shall see that it will be relatively simple to calculate the homology of a torus using singular homology, and it will be extremely simple if we use the cellular homology. Okay, so the point is, if you can grasp the idea of singular and cellular homology, then they give efficient results as compared to the simple shell homology. But once again, the advantage of simple shell homology is that for example, it's very algorithmic and we can use computer to calculate it. Okay, so moving on to lecture number 19, we started the new idea of singular homology. Of course, how we define singular homology, to define singular homology we needed a chain complex. Okay, so where the free abelian groups, okay, so the nodes are free abelian groups, so generated by singular chains, okay, or singular complexes. And then we discussed what is dimension axiom for singular homology. So as a matter of fact, we have been trying to see whether the singular homology satisfy the axioms of topology or not. Okay, so we haven't seen all of the axioms, that whether singular homology satisfy all of the axioms, but we have been trying to see some of the axiom whether singular homology satisfies or not. So moving on to lecture number 20, we once again discussed dimension axioms for singular homology, and then we discussed this functor Hn. Okay, so this is an important functor. Okay, so this is the second functor, the third functor that we encountered so far in this review. So the first two were pi naught and pi 1. Okay, so this is the fundamental group, and this pi naught is basically just saying that how many path connected components are there. And this is one of the most important functors, and this is going to be used for the rest of the course after this lecture number 20. So the functor Hn. Okay, so given any topological space, I can calculate Hn of x. Okay, so since it is a functor, then if I have a map, a continuous map between two topological space, then I should be able to calculate Hn of f. Okay, so sometimes we call it f lower star. Okay, so from Hn of x to Hn of y. Okay, so remember that Hn of x is going to be an abelian group, and Hn of y is going to be an abelian group, and so f lower star is basically a homomorphism between these two groups. Okay, and once again in lecture number 2 we discussed what are categories and functors. So that discussion helped us while trying to understand the properties of this functor. Okay, and in the last section of this lecture we discussed path connectedness and homology. So what's the relationship between path connectedness and homology? Moving on to lecture number 21, we discussed what is the relationship between homotopy and homology. So for example, we discussed that if there are two maps between topological space x and y, and let f be one map and g be another map. Now the point is, if f and g are homotopic, okay, then what will happen with their images under the functor Hn? So remember that we have a functor Hn from the category of topological spaces to the category of groups. Okay, now the point is, if we have a continuous function from x to y, then we should have its image. Okay, so we call this image to be Hn of f from Hn x. Okay, so a functor, remember that a functor not only give me the images of spaces, but it also gives me images of the maps. Okay, so Hn of y. Okay, now similarly I can have another image of G, so from Hn of x to Hn of y. So if f and g are homotopic, then these two maps are equal. Okay, so that's what we discussed mainly in this lecture, where we relate homotopy and homology. Of course, we discussed what is homotopy, and this helped us to understand homology as well. Okay, so remember that we started from fundamental group. Okay, so fundamental groups gives me a bridge between topological space and the groups. Okay, so if I already have one bridge, then why I'm proceeding with further relations between topological spaces and algebraic structures. So the idea is, as I told you earlier, that fundamental group fails at some point. So this fundamental group has some generalizations. Okay, so fundamental group is pi 1, but it has some generalizations, these groups. Okay, so these homotopic groups. Okay, so pi n. But the point is, these groups are extremely difficult to calculate. So what we did is we chose an alternative way. Okay, so which is relatively simple. Of course, it will be not as efficient as pi n, but it will be sufficient for our understanding of the topological structures. And the point is, given the fact that they are relatively simple to calculate, and that idea is homology. Okay, so we have been calculating the homology under this idea that pi n are difficult to calculate. Of course, they are extremely suitable to discuss the topological properties of a space, but then homology gives a good replacement which can be calculated as well. In lecture number 22, we discussed relative singular homology, relative homotopy axiom, and reduced homology. Okay, now as you know that if I want to define a simplicial homology or singular homology or cellular homology, then I can do it in one definition, or using one page of discussion. But the question is, can I calculate homology using that one page of definition of homology? So of course the answer is no, and that's what this all course is about. So we have been discussing tools which will help us to calculate the homology. Okay, so for example, in this case, a relative singular homology, which we also discussed in the simplicial homology case, relative simplicial homology. Okay, so this is one of the important tools. And then we discussed this relative homotopy axiom and reduced homology for the singular homology. So as I discussed earlier, that we will try to see that the singular homology satisfy the axioms of the homology. Okay. In lecture number 23, we continued our discussion of relative singular homology. We defined what is deformation retract. We defined reduced homology. Okay, so just a change in one of the nodes will give me this reduced homology. And excision and Meyer-Vittori's theorem and applications. Okay, so these two are extremely important tools, excision and MV theorem. Okay, so needless to say that when we are calculating the homology, then the main emphasis is on the tools which will help us in the calculations of homology, rather than trying to understand the definition, because the definition is we can just say that is kind of useless when we are trying to calculate the homology of different topological spaces. Okay, so these are tools like this, for example, excision and Meyer-Vittori's theorem, that helped us in calculating the homology of different topological structures. Okay, and then in this lecture we discussed some applications of these two important tools, and we also saw that how simple it becomes using tools to calculate the homology. Moving on to lecture number 24, we discussed free product of groups. Why we discussed free product of groups? So once again, after lecture number 1, where we discussed groups, we definitely we are going to need some other tools from the group theory. Okay, so with the passage of time we will be introducing these tools. So in this case we defined what is free product of groups, and why we defined this free product of groups, because we are going to need this in Van Kempen's theorem. Okay, and we can use this theorem for the calculation. Okay, and then we compare H1 and pi1. Okay, so this was one of the important discussions, in a sense that once again, as I said earlier, that we calculate Hn, the homology groups, as a replacement of pi n. Okay, so and why we calculate these things? Because they are relatively simple as compared to pi n's. And in this lecture we discuss the relationship between H1 and pi1, and we discovered that H1 hides some information that pi1 basically does not hide. Okay, so pi1 contains more information than H1. Okay, and then in the last section of this lecture we discussed equivalences of simplicial and singular homology. Okay, so as I said earlier, that simplicial homology and singular homology satisfy the axioms of the homology, so that's why it's just a method. We are calculating the same homology. So in this section we discussed that if there exists an object, if there is an object and the object is in such a way that we can calculate the simplicial homology as well as singular homology for that object, then that simplicial homology and singular homology are going to be the same, because once again we are calculating the homology, and these are just the methods for calculations. Moving on to lecture number 25, we started our discussion of cellular homology, and this is one of the powerful tools for calculating homology. Okay, after some topological results we defined what are projective spaces. Okay, because these projective spaces are going to provide us with some non-trivial examples for calculations of homology using this method of cellular homology. Okay, so we know that what is a projective space? It is just the collection of all one-dimensional vector spaces, or in other words we can say that if we are considering the affine space, then it is the collection of all lines passing through the origin of this affine space, or collection of all one-dimensional subspaces of An. Okay, moving on, in the last section of this lecture we discussed attaching a cell. Okay, so this is one of the fundamental operation of cellular homology, because this is going to give us the way of constructing a topological space. Okay, so we can attach a cell. Okay, so given any topological space X, and if we want to attach a cell, okay, so for example there is a disk, I want to attach this disk with this space X, then I need a map from the boundary of this circle to the space X. Okay, so let's say the map takes this boundary of disk to this part of X. So attaching a cell means just take the boundary of this and its image and glue them together. Okay, so once again, if you want to have a detailed view of this thing, so I would recommend that you go to lecture number 25. Okay, so how we glue it. Okay, so that's if you are interested, then go to the detailed discussion of lecture number 25. So we can attach this thing and it will become something like this. Okay, so some sort of hat attached to this space. So we have attached a cell to this space X. Okay, so similarly we can do this operation again and again, and we can construct some very non-trivial topological spaces. Okay, so very important procedure of attaching a cell. Okay, in lecture number 26 we discussed that what will happen if I attach a cell. Okay, so what will happen, in a sense, that what will happen with the homological groups of the space if I attach some cells. Okay, so then in the second section we discussed calculating homologies using attaching cells, homology of real projective plane. Okay, so using this idea we can calculate the homology of real projective plane, and then we can also calculate the homology of complex projective spaces. Okay, so once again, as I told you earlier, that this operation of attaching cells is going to give me a powerful tool for calculating the homology. Okay, moving on to lecture number 27, we discussed what are manifolds, and we also discussed what are CW complexes. Okay, so we are going to need these manifolds. Okay, so the point is the tools of algebraic topology can be used wherever there is a topological space. Okay, so the manifolds are basically topological spaces, so we can apply the tools of algebraic topology to manifolds as well. Okay, and in our further discussions, further lectures, we will see that we will see some results about manifolds, how we can use the tools of algebraic topology to discuss the manifolds. And then in this lecture we define what are CW complexes. Now what are CW complexes? This is you can say that it is a systematic way of attaching a chain of cells to obtain some topological space. Okay, this is the basic structure. So just like in simplicial homology we have simplicial complexes, so in cellular homology we have CW complexes. Okay, in lecture number 28 we discussed again what are CW complexes. In fact, we discussed some examples, and we also discovered that CW decomposition of a space is not unique. So in other words, there are more than one algorithmic ways of constructing a topological spaces using this attaching a cell procedure. Okay, so in other words, if I keep attaching cells to a topological space, okay, so further, so let's say starting from 0-dimensional to 1-dimensional, okay, so let's write it here, so up to so on, and I can go on to construct xn, and let's say this is our ultimate goal, to construct this x, but then there could be more than one ways of achieving this thing. Okay, so I can come through some other way. Okay, so n-1 up to so on, so y naught. Okay, so this y naught is totally different from x naught, but these are 0-dimensional. Okay, so there could be more than one ways of constructing a given topological space using this procedure, algorithmic procedure of attaching a cell. In the next section of this lecture we discussed what is degree of a map. Okay, so this degree of a map is going to help me to calculate cellular homology. Okay, and in this lecture we define what is a cellular homology. So this is the third and last kind of homology, or we can say that a method for calculating the homology that we did in this lecture notes. In lecture number 29 we define cellular homology. Okay, and we calculated cellular homology, and in fact we were convinced that if we can grasp the idea of cellular homology, and if we can understand the cell structure and the CW decomposition of a space, then cellular homology is very right choice. Okay, and in the next section we discussed what is homology with coefficients. So as a matter of fact, so far before this section, whenever we are discussing homology, then we are saying that the free abelian groups involved in the calculations of homology, whether it's singular or simplicial or cellular, so the free abelian groups are generated with coefficients from set of integers. Now the question arises that can we do it using some other groups, okay, so instead of integers? So the answer is yes. Take any abelian group and you can calculate the homology. Okay, so in other words, roughly speaking, I'm saying the following thing. So the free abelian group and these ni's belongs to Z, and these sigma i's could be anything, so depending on what kind of homology you are calculating, whether these are cellular or singular complexes or simplicial complexes. Okay, so and then when we try to define the homology with coefficients from some group, then we take these ni's to be from some abelian group G. Okay, so ni sigma I. So as a matter of fact, we didn't discuss this thing in a detailed way because we can do exactly the same steps in when calculating homology with coefficients. Okay, basically we also discussed what is universal coefficient theorem in order to calculate the homology with coefficients, and we discussed some examples over here as well. In the last section of this lecture, we started a new topic called the covering spaces. Okay, so this is the last topic that we discussed in this lecture, and this is an important topic because this will use the ideas of fundamental group and other ideas that we discussed so far. Okay, so to understand the topology and to use for example the idea of groups to understand the topology and to understand the fundamental group of a topological space. So a covering space has a very simple idea that if you have a base space, then a covering space is basically is x tilde such that there exists a continuous function from x tilde to x. So roughly speaking, we are just saying that take this base space x and take this sheet. Okay, so there are some collection of sheets. Okay, so x1, x2 up to xn up to so on. Okay, so each of this sheet looks like x. Okay, so here you can see an example that if you take s1 wedge s1, then we have some sort of two sheets over here. So this sheet is one s1 wedge s1 and this sheet is another s1 wedge s1. But we also saw that if I unfold this in a flat way, then it becomes something like this. Okay, so something like this. Okay, so this goes to something like this. So roughly speaking, okay, so remember that this x tilde has to be path connected as well. Okay, so and these sheets doesn't look like to be path connected, but it is a good idea to represent the covering space like this. So we have a continuous function from this covering space x tilde to x, and such that if I take an x in the base space capital X, and then there exists an open set U such that P inverse U is disjoint union of open sets. Okay, so if you take the inverse image of this, then on each and every sheet there is going to be an open set. Okay, so let's call it U1, let's call it U2, and it is disjoint union of these open sets. Okay, and this also tells me another thing, that P inverse of X is going to be a discrete set. Okay, because they are disjoint open sets, so that's why I can differentiate between any two inverse images. So let's call it X1 and X2. Okay, so this contains X1, X2 up to so on. So this is going to be a discrete set because I can differentiate between X1 and X2. So between X1 and X2 there is no other element. Okay, so that's why P inverse X is a discrete set. So in lecture number 30 we discussed covering spaces once again in a detailed way. In the last lecture of this course, we discussed what are group actions, okay, because then we were going to relate covering spaces and fundamental group using this idea of group actions, okay. So the idea of group action is very simple. You take a group G, then you can act this group G on Y. So the idea is how to act this group on some space Y, so to have a map from G cross Y to Y. If Y is a topological space, then we want this map to be continuous, okay. So if Y is topological space, then using this idea of group action, we can relate covering spaces and fundamental group, okay. So once again, notice that we are using some machinery from group theory, and we are relating these two concepts, okay. So using this idea of group theory. So in other words, throughout this course we have been using ideas from group theory, and of course modules and homological algebra and other algebraic machinery to discuss and to explore the topology of given topological space, okay. So topological spaces are so they are in every branch of mathematics. So whether you are discussing algebraic geometry or you are discussing differential geometry, so whenever you have a topological space and you want to discuss its topological properties, then algebraic topology is one of the important tools to discuss the topology of that space, okay. So last but not least, we have references. So mainly we have been following the first reference, An Introduction to Algebraic Topology by Joseph J. Rotman, and secondly we have been following these lecture notes as well, and thirdly we have been following these this book Algebraic Topology by Alan Hatcher, and on the fourth number we have been following the lecture notes on algebraic topology, okay. So on algebraic topology by Professor John Jones, and we have also been following notes for a first year graduate course in algebraic topology by Rob Thompson, and in the sixth we have been following the homology theory by K. Wandeli, okay. So we have been using some diagrams throughout this course, okay. So forgive me if I have not included some reference which I have used, okay. So mainly we have been using Wikipedia and some other references, for example Alan Hatcher and Differential Geometry by Barrett O'Neills and Topology, okay. So there are some other references as well, but we mainly use these references, and if you are interested in understanding other things other than we have discussed in this course, or you want to explore further the things that we discussed in this course, then I would strongly recommend you to go for the first and the third reference, okay. So Algebraic Topology by Alan Hatcher and An Introduction to Algebraic Topology by Joseph J. Rotman. So this is the end of the course. Thank you very much, and Allah Hafiz.